data projects. In particular, the team that I co-lead together with Davide here, the deep learning and big data department, which is the promoter of these initiatives, Meetup at Alchemy, let's say, which is a team dedicated to expanding Alchemy's data, machine learning, and deep learning services, trying to be part of the AI revolution which is at work, let's say, today more than ever before. Okay, so now I'll shut up. I will leave the stage to Leonardo, that will say a couple of words about the Science Milano, and then to Luca for the talk. Last but not least, at the end of the talk, for the people in presence, there will be the networking aperitivo, which is a courtesy of Clearbox AI. Thank you for the aperitivo, which is very important at this time of the day. So I will give the word to Leonardo, and enjoy the event. Welcome. Okay, so the first one is done. I will try to switch to the Leonardo presentation, which is this one. Perfect. I will go in presentation mode, and we are good to go, I think. I probably have to share again for the people. Okay, I think that we are good. So,
welcome again, everybody. Thanks for being here. Thanks to Alchemy for the possibility of organizing another event here. And thanks also, of course, to Clearbox AI and to Luca Gilli, that today gives us the possibility of grasping some knowledge about high quality synthetic data. And so I am very excited for this speech. I hope you are so as well. So just give me 2 minutes to present our meetup. So I'm gonna switch to the slides here. Okay. I don't know. Maybe it's not a good idea. Okay. Okay. Fantastic. We are an independent group of people, and the group was founded in 2016. So actually, last month was the 7th anniversary of our group. So we are very glad to reach this milestone. A technical community with more than 2,000 members, and today we welcome the new 45 people that joined us in the last few weeks, since the last meetup was held in Nexi. Sorry, Regia is calling me. Okay, so basically we are 8 people that you see here. A lot of them, like me, is here today, so we can chat together as well. And indeed, every one of us takes care of one of the different aspects of the organization of the events. But of course, there is always a call to action, because we want you to contribute to the growth of our network. So if you want to write some articles, get in touch for the organization of an event in your company, or if you just want to be a speaker with us, feel free to get in touch with us. We have all the previous recordings stored in our YouTube account that you find here, and then also on SlideShare. On SlideShare you can find all the previous presentations, so if you want to go and check all the materials that has been produced in the last 7 years, more or less everything, not everything, but a good percentage of it, you can find on these channels. And also the Medium blog, where you can find all the, okay, last time I moved, I will stay here. Okay, the content behind is cool for you. There is nothing relevant. So we also have the Medium blog, where we write a summary of the talk, and you will find also the talk of today in a few days. In conclusion, you can follow us also on LinkedIn, where we post all the updates on the events. So on LinkedIn, you will find all the details, all the schedule. You can find the links also to register to the new events. So if you want to join us, you can find also there our contents. And that's all. So if you want to propose yourself or your company to make a presentation, to share your knowledge about a data science application in your field, feel free to get in touch. And enjoy, and thanks again. I will leave the floor to Luca. Okay.
I will call Luca. So there. Share this. Working and is live. Okay, please, Luca.
Hello everybody, my name is Luca. I'm one of the co-founders of Clearbox AI. We are a small startup based at the University Incubator of Polytechnic of Turin. We are 3 years old, and we started on a slightly different topic, which is the topic of Clearbox AI. That's why the name Clearbox as opposed to black box. But during the last couple of years, we did a pivot towards synthetic data. So towards nowadays, we define ourselves as a synthetic data provider. And tonight, I wanted to share our experience, give you an introduction about what synthetic data is and what does it mean to generate high quality synthetic data. Maybe some of you are familiar with the topic of synthetic data. Synthetic data is fake data, fictitious data, so data which is not collected from real life events, from real life situations, but is artificially generated. The notion is that synthetic data is generated to be resembling as much as possible an original data set. So it's fake, but it should be as similar as possible to an original data set. There's a lot of talking about synthetic data. Last year, Gartner published a report stating that within less than 10 years, the majority of data used in data analytics and AI will be synthetically generated. The definition I gave you is very loose, so synthetic data can mean a lot of things. But according to Gartner, it's going to be quite relevant, and it's a trend that we are observing also ourselves as a company. While talking to organizations, we understood that there's quite some interest in synthetic data for two main reasons. So as data scientists, you might be aware that, of course, machine learning models need a lot of data. More examples make machine learning models more robust. So one point for synthetic data is to provide more examples to models to make them better. In case of issues with, for example, data imbalance or bias and fairness, one can think of generating synthetic data to fix these issues that are affecting our original data. So that's one point, and it's a very important point. Tonight I want to talk about something else, which is about data privacy. Because talking to organizations, especially in Italy and in Europe, we realize that synthetic data is seen as a very important privacy enhancing technology. The reason is that when we talk about individuals, there's a lot of regulation and data governance affecting what can and cannot be done to data if it contains individual data. And synthetic data is seen as a way to anonymize data, because you're not talking about real individuals anymore, but you're talking about synthetic examples. But when talking to organizations, we also realize that sometimes there's a lot of confusion about what is anonymization. When we talk about data collected from people's behavior, for example, behavioral data, that can be transactional data about GPS location or phone calls, there's a notion that if you remove the direct identifiers, the data is anonymous, which is actually not true. Like removing direct identifiers is called pseudonymization. So if you see this table, for example, is a table containing phone calls with locations where these phone calls were made. This table is pseudonymized because by looking at this table, you cannot recognize the individual. The name and the surname, maybe any direct identifier was removed. So this table per se doesn't give any information to a person just looking at it. But GDPR defines anonymous as a dataset that, in case of data leakage, won't give any extra information to an attacker that has malevolent intention. So, for example, if an attacker steals this data set and has some previous information about some people from this data set. So for example, he knows that a person made a phone call at a certain location at a certain time. This previous information linked to the pseudonymized table can lead to the attacker extracting further information. So for example, by knowing that this person made this call, the attacker might know the income of the person. That's something that you don't want to do from a GDPR point of view. That makes the data not anonymous anymore. Or for example, if you know that a person made a call at a certain time, and the attacker has this information, the attacker might profile this person throughout the dataset. So it might know that this person made several calls at several times of the day. And this is a big problem because it means that having really anonymous data is really difficult. From a GDPR point of view, you have to demonstrate that in case of data leakage, attackers cannot construct extra information about the individuals containing this table. And usually data protection officers demand that these tables are anonymized by aggregation, so by making talking about group of individuals instead of individuals, or binning, so making the location much more discrete from a resolution point of view. And that, of course, destroys a lot of information because you are basically anonymizing the data by masking and destroying information about what an attacker can do. From this point of view, synthetic data is seen as a way to create a dataset which has the same properties in terms of granularity and resolution as the original dataset, containing fake individuals. So individuals that are not existing in real life and that won't give any information to an attacker, but you have to demonstrate it, of course. There's a lot of talking about these aspects. The European Union, of course, talks about it as a privacy-enhancing technology. The European Data Protection Supervisor, which acts as a sort of guarantee of privacy, as a privacy observer for the European Union, says that synthetic data is a way of anonymizing data, but of course you have to, as I will show you later, properly demonstrate it. You have to ensure that synthetic data is actually anonymous. So there are these two main aspects about synthetic data: how to make synthetic data can make models better. Synthetic data can be used as a privacy-enhancing technology. Today I want to tell you a little bit more how to create synthetic data, because the definition I gave you before was very vague. It's fake data created to resemble as much as possible an original dataset. But there are indeed a lot of techniques to create synthetic data which is actually realistic looking and useful for a given purpose. There's a first approach, which is creating data from scratch. In case you don't have any original data set, any original data source, the idea is that you can inject your own expert opinion about how the data should look like. And this can be done using simulations, rendering. In case you're talking about images, you can use 3D engines like Unreal Engine or Unity 3D to create fake environments, fake people. For example, last year, Unreal presented this new tech demo of their engine with a tool called MetaHuman that generates images, rendering of people which are absolutely photorealistic. And that's a way of generating data. Another way is by using simulations or by using agent-based modeling approaches, where as an expert you might think, okay, I know what the data should look like. I will try to. I know what the data should look like, and I will inject my own opinion, my own experience about what the data should look like into these simulations, and create these synthetic scenarios, which are basically, for example, you can think of creating a transactional histories by simulating users' behavior. I repeat, by injecting your own idea of what a user behavior should be, but that does create data sets which can be useful for a purpose. The other approach is when you do actually have some original data to synthesize from. So the idea here is that you do have a data set. It can be a database or a set of images or the environment. You can fit a probability distribution on this data. So data is usually distributed according to probabilities. For example, if you're talking about individuals, the probability of an individual having a certain age, a certain degree, a certain job are related to each other. An 18-year-old maybe won't be married or won't have a master's degree. So this kind of knowledge about the probability distributions can allow you to fit new distributions that will allow you to sample from. So the idea here is to literally fit a model to create new data points, to be able to sample new data points. In machine learning, there is a very big family of models, which is the generative family of models, which is becoming very popular nowadays because of all these examples in image, also text generation. And there are a family of models from statistical machine learning that learn how to sample new points given the knowledge they learn about the probability distributions characterizing these points. So the idea is that they learn joint probability distributions, so the probability of a point occurring in all its features, in all its individual components, and they're usually separated from another big family of models, which is the discriminative models. As machine learning experts, you might be working with supervised machine learning, for example. Supervised machine learning is a discriminative approach because you learn a conditional probability, the probability of a target being assuming a certain value given the input. With generative models, you actually learn the joint probability of all the inputs assuming a certain value at a certain time. So, for example, if you take a very silly example of an animal population, it could be an animal population containing cats and dogs and squirrels, etc. The generative model learns that the fact that a cat has a certain color, has four legs, has short fur, whiskers, has a certain probability of occurring. So from that, you can actually you have the knowledge of being able to sample new animals based on this kind of knowledge of the likelihood of an animal assuming certain characteristics. With discriminative models, you just learn that a cat is a cat if maybe he has a tail or whiskers. So it's much more easier, of course, to train a discriminative model because they actually need much less information to make this kind of discrimination between classes. Generative models are much more challenging because you need to be able to understand that the combination of all these parameters has a certain likelihood. That's the most challenging part. Now I made an example with animals, but these notions can be applied to any kind of data. For example, if you have an image, a generative model will learn the probability of a pixel assuming a certain value given the values assumed by the other pixels in the same image. And of course, they're very, very challenging to train. They're not a new idea. People have been using generative models for decades. For example, Gaussian mixture models are generative models because when you do clustering, instead of training a model to assign a label for a given cluster, you train a model that learns that the clusters are distributed according to some Gaussian distributions. So you create a model that learns how to sample new data points and the likelihood of a point being associated to a given cluster. So the notion itself is not very new, but the advances in the computational power that was introduced in the last 10 years changed things quite a lot because the generative model became much more powerful at generating complex data. So until 10 years ago, they were used for very simple applications, for example, Gaussian mixture models. Recently, 5 years ago, they introduced the concept of GAN, this generative adversarial network, which was a network architecture which was actually very good at synthesizing points which were very realistic. So they applied it to images until a few GANs were introduced in 2017. Until 2016, image generation was very subpar. It was all the examples were, for example, very blurry. When they trained these GANs, they demonstrated that they could generate images which were extremely realistic using this kind of generative approch. This image, for example, was presented in 2017 with this style GAN paper. But that's what opened the floodgates for generative AI because they basically demonstrated that something that was conceived to be really, really difficult until a few years before it was actually possible. And the concept of GAN was quite interesting. So they demonstrated that they could train a generator architecture to generate new samples by making them realistic by making it compete with another architecture, which was a discriminative model. It was trained to discriminate between fake points and real points. So the training of this kind of generative adversarial network is called adversarial because you have these two architectures that compete with each other. One has to make these points as realistically looking as possible. The other has to make to understand whether a point is real or fake. And this training process demonstrated to be very effective at allowing people to synthesize data with this kind of very complex characteristics. They're not the only generative model. Like now, maybe GANs are becoming even a bit too old. In the meanwhile, people have been playing with variational encoders. Nowadays, everybody is talking about diffusion models. For example, Stable Diffusion is a generative model based on this kind of diffusion approach. But all these kind of approaches have the characteristics that they learn how to allow people to sample from known distributions. So, for example, in all these points, the models learn to compress the data into some kind of a representation, which is tractable. So usually, for example, for rational encoders, these are Gaussian distributions. We know how to sample from a Gaussian distribution, and this kind of being able to sample from distributions allows to sample the actual complex distributions. And this kind of approach is quite common in generative AI. So this kind of learning a representation and learning how to sample using a simplified distributions. And diffusion models, especially with stable diffusions, have become extremely popular in image synthesis. And even the approach is that you can train, you can add noise gradually to an image or to a data point. You can train a model to denoise this kind of image according to a certain strategy. And this kind of process allows you to sample from white noise and create realistic looking images by training this architecture to deconstruct images from white noise. That allows you to sample realistic looking points. But the problem here is that, okay, it's true that we can train generative AI models to sample realistic looking points. We demonstrated that this is actually possible and can generate very, very realistic points. The concept is that how do we transform this into synthetic data sets? Because it's not enough to generate, to be able to generate points, but when we talk about data, we talk about something that actually will eventually be used for something. So we might use data for machine learning or data for data analytics. We might have different ideas on how to extract the information from this data. The concept of synthetic data is that how do we actually use this kind of generative approaches to generate something that is actually useful for our intents. And that's what actually defines synthetic data as a product. Because now you do have something which is a generative model, which is something that is part of a bigger picture. But when you generate synthetic data, you need to demonstrate if this data will be actually useful for something. So it's not a matter of generating a single point, but it's a matter of understanding what is the situation of what do this point that is generated actually contain in terms of information, in terms of quality, in terms of content itself. So when generating synthetic data, there are two main concepts. You need to be able to demonstrate that it's actually useful for something. You need to measure this kind of concept of data utility. If I generate this data and I give it to you, telling you that it's synthetically generated, it's safe, and you can use it, you have to have the notion that you can do it, and you need to generate a lot of reports about the quality of this data. At the same time, if you use this kind of approach to generate data which is actually anonymous, the data that you can actually share freely, that you don't worry about, for example, or identification, you need to demonstrate that it's the case. And it's not always so trivial as I will show you. So, for example, one very important test that we can apply to synthetic data is the notion of train-on integrity theory. Assume that you have a generative model that generated a number of data points that can be images or tables or time series. The notion of train-on integrity theory is that, okay, I have this synthetic dataset. I can train a model on this synthetic dataset. And I can test this model on some holdout metrics, some holdout data, some data that was never touched by generative model. At the same time, you can train a model on the real data. You can compare the performances of the two models. And the hope is that if the synthetic process was actually good enough, the performance metrics will be actually comparable. If you give a model if you give synthetic data sets to a division to train a model in it, the model trained on it will be actually good from a metrics point of view. And that's actually a very global score. It gives you a very good idea about how well a synthetic data set is doing. You can dig deeper into this kind of analysis because you can, yes, compare the metrics of the two models, the synthetic and the real model, but you can also compare how these two models behave. So the idea is that you might have models that have similar metrics. You want to make sure that they base their discrimination on the same predictive signal. So you can compare, for example, the feature importance of both models to understand that actually if a model is classifying a positive label, it's doing it by using the same features. So you can also perform this kind of interpretability analysis of the two models to make sure that the synthetic data is actually teaching the right stuff to the model. And that's also very important because you want to be not only use a very global metric, but to demonstrate that the insights of your data are actually similar. Another concept comes from this notion of a GAN. In the same way, these generative adversarial networks have been trained using this kind of discriminator that discriminated between fake or real. You can apply the same kind of test to synthetic data. So you can say I can train a model to discriminate between real data and fake data by labeling, for example, the synthetic data set with a 0 and the real data set with a 1. You find yourself with a classification problem where the labels are 50-50 distributed. You can see how a model performs when given this task. And the objective here is that if your synthetic data is good enough, the model will be as confused as possible. So if you have a model that is actually able to discriminate very effectively between real points and fake points, you have a problem because it means that there's something that is giving away the synthetic data. And even in this case, you can yes, look at the global performances of this discriminated model, but you can also look at if the model is doing well. If there's something that is giving away the data, you can look at the insights of the model, like using a feature importance or any interpretability analysis to understand what of the synthetic data is giving away the fact that it's fake. And you can actually do this kind of analysis to improve the synthetic data itself. And these are two scores which are very global. They can be analyzed more easily by doing this kind of interpretability analysis. There's a problem because these scores have a very strong limitation in the sense that if you both scores are based on comparing synthetic data and real data, the limit where you compare real data with another dataset, which is let's call it synthetic, but it's simply the same dataset but reshuffled, you will obtain perfect scores because the data is actually the same. So the models won't be able to discriminate. The training synthetic is real will be super performant because you actually bring the same information, and that's a problem because you don't want synthetic generator spitting out the same data as the original one. And generative models are known as machine learning models to have problems related to overfitting, for example. If you train a generative model too much on the data, you might find yourself in a situation where the model actually learn how to reproduce the same images or the same points as the training dataset. And for this stable diffusion example, like this model able to generate images from text prompts, some researchers a couple of months ago demonstrated that it was possible to retrieve the very same images that were used to train the model as prompts. So the generative model was actually generating images which are really basically the same. And this is a terrible problem to have because, for example, if you're using synthetic data from privacy point of view, that's something that you want to avoid. It's a catastrophic situation because you don't want your generative model to spit out real individuals, for example. And in this case, this topic is really also related to the privacy issue. So you want to demonstrate, yes, that your synthetic data contains enough information signal that is distributed in the same way as the original one, but you need to demonstrate that the synthetic data is actually new data. It's not simply the same one spat out by the generative model. And here enters a second set of test analysis you can perform on the data itself. And in this case, you want to, as I said, demonstrate that the synthetic data is actually new. And there are different ways of demonstrating this aspect. The most common is to think about the fact, like if you reason from a privacy point of view, the fact that an attacker is coming into possession of your synthetic data after a data leakage is something that happens. Instead of stealing the original data set, they stole the synthetically generated one. You can understand what the attacker can extract from this data about the real individuals. The ideal situation is that the answer is cannot extract any information, given the fact that is in possession of they're in possession of this data. But there are a lot of tests and metrics you can also do to quantify this task, and most of them are based on the concept of distance. So the idea again is to keep some validation or some holdout data aside that has been never touched by the generative model, and you can compare the synthetically generated dataset both with respect to the dataset which was used to train the generative model and to this data which was never touched before by the generative model. The idea is that by comparing distances with respect to these points, the synthetic data should not be systematically closer to the training dataset, because it means that the model has learned too much about the original data. You don't want the situation because this situation might lead to too much information available to a potential attacker coming in possession of the synthetic data. So this is a test that can be implemented fairly, in principle, fairly easily, depending on the kind of data you are dealing with. If it's databases or images or time series, the main problem here is defining the concept of distance, because if you work with models like nearest neighbors, you might know that defining a distance is not trivial, especially if you have points containing categorical and numerical data. Like if you have two individuals, what's a good way to define the distance between these two individuals? If there were only numerical variables, you might say it's just the Euclidean distance between the numerical variables, but the fact that you're in presence with categorical data makes things a bit more complicated. So you need to devise some distance metrics which are robust enough for every problem to make sure that you're able to assess this kind of privacy properties, which also translate in the fact that the data is actually new. It's not simply the original data slightly changed or slightly perturbed. And this kind of once you have this distance, you can actually plot how well your synthetic data is doing. So, for example, this kind of the orange histograms are the distances between the synthetic data set and the holdout data, which was never touched by the generative model. The blue ones are the distances between the synthetic data and the training data, which was used to generate the training model. And here we have a situation where the synthetic points are really too close to the training dataset, which means that something went wrong in the training process. And the generative output might be not so good, because you're basically spitting out very similar information. You're not adding anything new to the data. And you want to find yourself in a situation where these kind of distributions, so these systematic distances between the holdout and the training, are actually comparable. In this case, the synthetic points are representing something actually new. And even if you're using you can demonstrate it is safe from a privacy point of view, but even if you use it from a data augmentation point of view, it means that you're actually adding new information to the problem. You're actually making the model, let's say, more robust. And this is, I think I can go a little bit further. This is a very important aspect. So how to make this kind of analysis robust, because on one side you have the utility. You have to demonstrate that you're preserving enough information on your synthetic data. There's the extreme case where if the data is actually a clone of the original one, you have a maximum utility. So you need to add this kind of metrics which are privacy-based and distance-based that are really tricky to define depending on the use case, on the data type you're dealing with. I've made this example about tabular data, but if you had images, for example, the same image slightly shifted towards that direction, might give you a very far distance if you use a Euclidean distance, and that's a problem because we are actually having the same image, and that's probably the most challenging part about evaluating synthetic data. So how to make this kind of metrics work together when you want to, for example, optimize the generative architecture. And I also wanted to show you something about, since I have a few minutes, something about, before I was showing you how to use synthetic data for privacy. But synthetic data can actually be quite good at a certain task, which is the auditing of machine learning models. Usually, when we write machine learning models, we are writing software, right? It's a software that contains a machine learning inside. But with software, we are used to best practices such as unit testing. It's something that comes from the field of DevOps. We know how to understand if a software is properly written. The same concept can be applied to machine learning. Machine learning is just a component into a bigger software picture. We can apply the same concept of DevOps, so we can think about using synthetic data as test data for machine learning. It can be used very effectively for interpretability of the models. Like Google published a couple of 6 months ago a paper about using synthetic data to interpret models. So the idea was like to have a classifier that you want to explain. You present the classifier with different variations of the image that classifier that you want to get a local explanation about. And this kind of perturbation can give you an insight about how the classifier is working. So in this case, it's really related to understanding model behavior. So you understand that if I change the dimension of the ears, the classifier won't see it as anymore as a cat, then it might tell you something about how the classifier is behaving. But in this case, they use a generative model, a GAN, to systematically generate this kind of perturbations that might help users understand the model behavior. Another application is, I think the video got stuck. Every time there's a video in a presentation, there's a example for text models working with text. The idea is there's a very interesting paper about how to evaluate. Sorry, I think the video made everything crash. About how to evaluate sentiment analysis classifier, like using this kind of software-based approach. Yeah, and there's this very interesting paper where they really said, okay, what shall we do to implement the same kind of best practices we adopt in software when understanding model behavior? And they created this kind of checklist. So a way to test models. In this case, it was text NLP models. So, for example, if you have a model classifying sentiment, or a model understanding whether a review is positive or negative, you might have some kind of test you want to write about this model. So if I change a double negative, then becomes a positive, or if I change in the review allocation, the review shouldn't change because the review shouldn't be based on the location. And all these points are synthetically generated data points. So there are points that were not existing before, points that you're creating from scratch to understand the model behavior, but points that are actually useful to understand how a model is actually working. The same in digital healthcare. There are a lot of examples nowadays coming out about using synthetic data to explain models. So before giving the models to a doctor, that might be used for making like a decision process easier, you want to audit this model properly, and this kind of auditing can be done using synthetically generated points. So if I have an image that represents a disease, a certain disease, synthetically generating an image starting from the original one sane might give you some idea about why the model classified an image as a disease. So this kind of perturbation-based analysis, which is obtained using generative AI, which is really promising in terms of model auditing, for example. And it's more or less what I wanted to show you tonight. It's the fact that CTT data can have this kind of double utility in terms of machine learning, of course, but also in terms of privacy. But the most important part is that synthetic data is not just training generative models, but is actually being able to analyze the data you generate from a utility, but also to properly measure how new the data is compared to the original one. And that would conclude my my speech for tonight. I hope you have a lot of questions. Yeah.
So, question. You have a very more data in which you suspect that there are bias.